Good. Good morning, everybody. Welcome
Hi,
back. Hi, Lydia. Welcome back to Galois theory. It's an exciting day because today we're going to get into some actual Galois theory stuff. Woo! After we talk a little bit more about and finish up our discussion of irreducible polynomials. So, you can do irreducible polynomials, and then we're actually going to start building up using kind of all of our background tools towards some actual Galois theory by defining field extensions today. And I hope everybody remembers their linear algebra.
Oh, I love
linear algebra.
I've got my usual office hours for the next few days. Thursday, or this afternoon, 1 to 2. Tomorrow morning at 11, and Monday at 11 and 1. Don't forget to all have a homework for due on Tuesday. It's mainly focusing on playing around with factoring polynomials and such. Any questions or comments for it? Any questions or comments before we get started for today? Bart?
What is Seamus eating?
Seamus, what are you eating?
It's a breakfast bowl.
A breakfast bowl.
What are you eating?
Great
Glad
question.
to go
Hold on, there's too much discussion. What was it?
I have a comment. I'm glad we're starting Galois theory.
Yeah, you know. Glad we're starting actual Galois theory now that we're like over a third of the way through the semester. Yeah, well, technically everything we've been doing is like a build up to Galois theory. It's not like we've just been wasting our time. A lot of you have tried your best to make us do that in this class, but I try to keep things on track. But no, once we get into field extensions, we'll actually be steadily building our way up towards fundamental theorem of Galois theory. Yay! Alright. What is the 0 say to the 8?
Oh. Nice belt.
Nice belt! Yeah! Okay, so when we left off last time, we talked about Eisenstein's criterion for a test you can use to find irreducible polynomials. We played around with that some, talked about some tricks you can do with that, got a little bit sneaky. And then towards the end of class, we also introduced this other trick, which helped us determine if a polynomial is irreducible, which basically says, take your polynomial, reduce it, mod p, meaning reduce all of its coefficients mod p, and then assuming the overall degree of your polynomial doesn't change when you reduce it mod p, if the mod p polynomial is irreducible over z mod p, then the original polynomial, turns out, will have to be irreducible over q. So last time we talked a little bit about this theorem, worked through an example of it, showed that the converse was not true. If f of x is irreducible over q, that doesn't necessarily mean f of x bar will be irreducible over z mod p. But we haven't actually proved this theorem yet, so I want to start class off today by taking a look at that. And it turns out the proof's not actually that bad. You basically can just do it by contrapositive, show that if f of x is reducible, that will necessarily tell us that f of x bar will also be irreducible over z mod p. If f of x is reducible, no I, other than the in reducible, no I up front, then f of x bar will necessarily be reducible.
Got it.
So let's do that. So we're going to start off by supposing that f of x is reducible. So we have some integer polynomial that is reducible over q. And then, well, that means we can factor it into two non-constant factors. So let's do that. So we'll write f of x is going to be equal to some g of x times h of x, which for some g and h with the degree of g strictly smaller than the degree of f, and ditto with the degree of h. So what it means to be reducible is that you have a factorization into non-constant terms. And then what we're going to do is we're just going to take this equation and reduce both sides mod p. which will tell us that in, check it out, Parker, this polynomial ring, where all of our constants out front are being taken mod p, what can we say about f of x bar? Well, by definition, that'll be g of x times h of x, with a big old bar over the top of that.
But wait,
But wait, Seamus, what can we do with this expression?
multiplication works nicely over polynomial rings with modular arithmetic.
Reducing mod n works nicely with respect to multiplication, in other words.
Yeah, that's a much better way of saying that.
And addition, for that matter.
Addition too.
Which means, how can we rewrite this?
You can rewrite it as g of x bar times h of x bar.
Hey, imagine that.
Woo!
So would you look at that? If f of x bar has a factorization into g of x bar times h of x bar. So, question. When we reduce everything mod p like this, do we know g of x bar and h of x bar are both non-constant? Could theoretically be the case that even if these are non-constant up here, when you reduce the mod p, maybe all the terms but your constant term, or even the constant term goes away.
So if all the terms, including the constant term, go away, then wouldn't f of x just go away too?
Essentially. And here's where we're going to have to rely on this condition. Get out of here with your dots. So, first of all, let's take a look at the degrees of each of these. So, the degree of g of x bar, well, when you reduce something mod p, when you take a polynomial and you reduce it mod p, we know its degree could potentially get smaller. Like if we were to take, for instance, 2x squared plus 5 and reduce that mod 2, that would just come out to, a constant polynomial in that case, because the 2x squared is equivalent to 0x squared there. So when we reduce mod p, our degree can potentially get smaller. Can the degree even get bigger by reducing mod p? Wouldn't really make much sense to reduce mod p and suddenly have our 0x to the fifth term suddenly became a non-0x to the fifth term, because modular arithmetic doesn't work that way. So we can guarantee this is going to be less than or equal to the degree of g of x. Which, by assumption, is strictly smaller than the degree of f of x. Which in turn is equal to the degree of f bar of x. Why this? Because that was one of our original assumptions in our theorem. So what does that tell us? Well, it tells us that the degree of g of x bar, whatever g of x bar turns out to be when we reduce everything mod p, it is going to have to be strictly smaller than whatever the degree of f of x bar is. So far, so good? Okay, so we know the degree of g of x bar is strictly smaller than the degree of f of x bar. So what can we say about the degree of h of x bar? Eleanor?
It's also strictly less than the degree of f of x bar.
Why?
Because you multiply h of x and g of x to get the same degree as f of x bar.
Yeah. Or you could just say literally the exact same argument, just replace your g with h.
Yeah.
That would work. but what you said works too. I'm just gonna say then that, or no, not that. And that, similarly. And if both g of x bar and h of x bar both have degrees strictly smaller than f of x bar, can either of these be, can g of x bar and h of x bar, can either of those be constants? I would say not, because if either of these was a constant, then it would have degree 0, so the other term in this factorization would have to have the same degree as f of x bar. But since both of these have degrees strictly smaller than f of x bar, that tells us neither of them can be constant. So thus, g of x bar and h of x bar are non-constant, hence f of x bar is reducible. In Z mod D. So what does that tell us? If f of x is reducible, then f of x bar has to be reducible. Flip that around, take the, dare I say, contrapositive of that, and what do we get, Lincoln?
If f of x bar is irreducible in Z mod P, then f of x is irreducible over Q.
Yeah. Since f of x reducible means f of x bar is reducible, that means if f of x bar is not reducible, meaning irreducible, that would imply the original f of x had to have been irreducible as well. Technically over the integers, but as we've seen for an integer polynomial, being irreducible over the integers is equivalent to being irreducible over the rationals. That was Gauss's lemma that we talked about last Tuesday. No, last Thursday. Today's Thursday. Hold on.
Oh, what?
Hey,
We're all the same.
questions or comments about this theorem?
It's a nice theory.
Is what?
It's a nice theory.
It's a nice theorem. Lets us get away with results.
I think it's the first time I've heard somebody compliment a theorem.
It's a nice, theorem. Theorem, you look at my side today.
Whoa.
So let's do an example.
I'm writing that down.
Let's do one more example, and then we'll move on to the next packet. So I'm on the back page. I want to look at g of x equals 7x to the fourth plus 10x cubed minus 2x squared plus 4x minus 5. I'm going to show this thing's irreducible over the integers.
We should use Z mod 3.
We should use Z mod 3.
Why? That doesn't do anything.
Wow, Eleanor takes.
I tried Z mod 2, it didn't.
Oh, Z mod 2 didn't work.
Well, Z mod 5 didn't work.
Oh,
You
Z mod.
tried Z mod. I.
Oh no, it looks like we'll have to try Z mod 3. Well, before we try doing that, can we just use Eisenstein on this thing as currently written?
No.
No, there's no primes that divide 10, 2, 4, and 5. All of those.
Just need to change that.
Well, if we change the constant term, then I guess we could probably get away with it. But I want to do one of these type problems, not one of those type problems. So,
Wait,
Eleanor, what's that? Jonah?
whatever. I was wondering.
Get your thoughts together and come back in. So, we're actually going to reduce mod 3. I think that's right. So,
It didn't work.
Well, yeah, but then none of them are factors.
None of it goes away.
But then you get something that you could.
I want
so reducing mod 3 is going to give us what?
X to the fourth plus x cubed minus 2x squared plus x minus 2.
What do I see
Oh,
here?
stupid.
Oh my.
I forgot minus 2 equals 1.
That looks like the thing that we talked about
The thing?
before.
Oh, hey, that looks a lot like that
The
cyclotomic thing.
Cyclotomic,
Yeah, what did we show about that?
The fickle
They're
The
irreducible.
what?
They're irreducible
The cyclotomic.
over Q in the
Yeah.
integers.
My brother.
Not-
We didn't say irreducible over Z mod 3.
Can we just do it again?
No,
That doesn't make any sense.
I'd rather.
We only have 3
I'd rather
numbers
not.
to check, let's just plug them in.
Okay, so what do we get if we plug in 0? We'll get
1.
0, well, we get 1. I'm not gonna bother writing it. 0 plus 0 plus, shut up. What do we get if we plug in 1?
2.
1, 2, 3, 4, 5, mod 3 is 2. What do we get if we plug, please stop. Plug in our last one, we plug in 2.
1.
Oh god, oh
Let's
my god.
replace them all with minus 1s. Let's plug in minus 1 instead.
Wait, what?
Yes, plug in negative 1 instead. It's much easier.
2 is congruent to negative 1 mod 3. So you get like negative 1 to the 4th becomes 1 minus 1 plus 1 minus 1 plus 1 comes out to 1.
Whoa.
Or you could actually just plug into, it's not that hard, 2 to the 4th is not a big, it's 16 plus 8 is 24, plus 4 is 28, plus 2 is 30, plus 1 is 31, 31 mod 3 is 1.
Or you can just reduce along the way, and 2 to the 4th is 1, and 2 to the 3rd is 1.
Lots of lovely ways of showing that this does not come out to 0, which is the moral of the story here.
Why doesn't Z mod 2 work? Or
I don't know, because, I don't know, Emily Rose, why didn't Z mod 2 work?
It reduces down to x to the 4th plus 1, and then when you plug in 0, you get 1, and when you plug in 1, you get 0, so there must be a root in mod 2.
Oopsies. It's because if you try and reduce, it's because if you try and reduce this mod 2, what you'll end up happening is that f of x bar is reducible over z mod 2, not irreducible, so this theorem doesn't tell you
so
anything.
you're basically just trying to snipe an instance in which it's not.
Correct. Hint, z mod 2 though might be a helpful one to check for the homework problems.
So does that mean that,
Ooh.
that most numbers will work?
That most numbers will what?
Will work, if it's just anything where it's not reducible.
Any p that you can find that satisfies all of this will get the job done. Then there's a lot of, there's infinitely many primes. You can check all of them, and I won't say most of them will get the job done, or
I mean, what's the problem is if it would be reducible, that would probably shouldn't happen for too many primes.
I'll give you a hint. The ones I gave you in the homework, you should be able to get with very small values of p for things you do this for.
Just try
Computers
run
can
a
get
prime
big
and
keys.
test all the cases.
Computer, let's continue. So, hey, this thing has no roots. What does that tell us?
It's irreducible over 2.
That tells us it has no linear factors.
Oh, right.
But that technically doesn't tell us irreducible because with degree 4 and higher, you can have reducible polynomials that still have no roots.
Right.
It can factor into quadratic times a quadratic, for instance. This tells us g of x bar has no roots, it's no linear factors. But if you're in degree 3, that would be, if you had a degree 2 or a degree 3 polynomial, that would be enough, because the only way for a degree, let's say 3 polynomial to be reducible is into degree 1 times degree 2. And if there's no degree 1 factors, you're done. But you could have degree 2 times degree 2 give you degree 4, and have this split into 2 irreducible quadratic factors, even if there's no linear factors. So, we still have some work to do. So I'll say, so if g of x bar is reducible, it must be meaning we would have to have g of x bar which is x to the 4th plus x cubed plus x squared plus x plus 1, would have to split into, I don't know, something of the form x squared plus ax plus b times x squared plus cx plus d. James?
Maybe we should just multiply those out.
Oh,
Would you need coefficients to start with x squared?
do we?
We could just
I
use
think
the work
if
if they wanted
out to.
Or we can know because x4 has that.
Well, we could theoretically have something like that going on, because 2 times 2 mod 3 is 1.
But then you could take negative of each one.
Then you just take the negative of each one, and it reduces down to you can assume that they're both
So that only works because we're mod 3.
correct.
Okay.
Yeah, if we weren't mod 3, we'd need coefficients here, but this problem's going to be computationally messy enough as is. So it turns out. Yeah, the leading coefficients either both have to be 2, i.e. negative 1, or they both have to be positive 1, because there's no other way to multiply 2 elements in Z mod 3 to get 1. But, so keep in mind that depending on what your Z mod n is, you might need terms out in front here. All right. Oh boy. Let's do some multiplication. Let's do some big old foiling. So if we were to compare x to the 4th terms, we get 1 equals 1. Great. What's going to be the x cubed term we get when we multiply out these 2 quadratic terms?
C plus a times x cubed, I think.
Yeah, so for degree 3 terms, we'll get ax cubed plus cx cubed has to be equal to x cubed, which is the same as saying 1 equals a plus c.
But are we working in, so one of those has to be 0.
One of these has to be 0? Well, they could both. Why not?
Oh, wait, no.
They could both be 2.
Never mind. Dang it.
Oh, if only life was that simple, Eleanor. And got to keep in mind, all of this, I'm not explicitly writing out addition in bars. It's or like plus like a 3 down here each time. But we got to remember, all of this from this point on is taking place in Z mod 3. So saying a plus c equals 1 doesn't mean what you think it means. How about the degree 2 terms? A little bit trickier, but not too bad. Lincoln?
AC plus B plus D.
And on this side we get 1, so we get 1 equals AC plus B plus D. How about our degree 1 terms? Isaac?
You have an AD plus a BC.
1 equals AD plus BC. Again, all of these are being equal to 1 because we're just equating coefficients here with coefficients here. And literally all the coefficients over here are just 1. We have 1x to the 4th, 1x cubed, 1x squared, 1x, 1. And finally, how about our constants? I'll do, what's that?
BD.
Yeah, beady. He's got some beady eyes there.
They look like glasses a little bit.
A little bit. It's got something like sticking off of. This one's got like something sticking off of it, but yeah, kind of.
Like a little bit.
All right. We want to show there is no A, B, C, and D that satisfies all of these.
Ooh.
Because if we can show there's no A, B, C, and D in Z mod 3 that satisfies all of these, that means no factorization like this will work, which means it's irreducible over Z mod 3, which means this is irreducible over the integers.
This is the.
Which means this is irreducible over
This
Q.
is the linear algebra.
Can we make a matrix?
You want to make a matrix?
Look at AD plus BC. Isn't that just so reminiscent?
Oh yeah, that kind of feels like it. Well, AD minus BC
Yeah.
is at least.
Yeah.
And we're not in Z mod 2, so addition is not the exact same as
Not the
subtraction.
exact same, but it's close enough.
Let's play around with some of these. So 1 equals BD. What does that tell us about B and D?
I think it says either they're both 1 or they're both 2.
The only way to multiply two coefficients together in Z mod 3 to get 1 is 1 times 1 and 2 times 2. Okay, so we get B equals D equals 1 or B equals D equals 2.
And C, A plus C, either both of them are 2, or 1 is 0 and 1 is 1.
Yeah, okay, so we sub that in here and say, hey, that's going to tell us then that 1 equals AC plus 1 plus 1, so AC equals 2. Or 1 equals AC plus 2 plus 2, so AC equals, what's 2 plus 2 is 4, mod 3 is 1, subtract 1 from both sides to get 0.
Because in the New York congruent, we can factor B out of the degree of 1 equation.
Yeah.
And then we have B times A plus C, but we know A plus C is 1. So then we have B plus C is 1.
We have A
You're
plus
going to
C.
need to say that a lot more slowly for me
We
to
have
do
A
follow.
plus C equals 1 above.
Aha, but
Well,
A
we
plus
have
C
that.
equals 1.
Yeah, but then you know B equals 1.
There's lots of ways you can approach this. I think if AC equals 2, you can get a contradiction here pretty quickly. Because if AC equals 2, what does that mean what A and C have to be?
1 and 2.
1 and 2 respectively.
Oh, wait, plus 2 doesn't equal 1.
Oh no.
But then A plus C equals 0, which is not equal to 1. So get that out of here. And also get that out of here. So we would have to be in this case. AC equals 0. So if AC equals 0, what does that tell us? Lincoln?
Either A is 0 and C is 1, or vice versa.
Why does it tell us C would have to be 1 if A is 0?
Because of the degree 3 equation.
Okay, yeah, okay. Well, if you combine that with, so this just tells us that A equals 0 or C equals 0, and then when you combine that with here, we get A equals 0, C equals 1, or C equals 0, A equals 1. Okay, so let's look at each of those cases. So B equals D equals 2 is kind of required by what we've seen so far. And let's look at the case of A equals 0, C equals 1. Does that satisfy all 4 equations?
Well, let's look at AD plus BC.
Okay, AD plus BC would come out to 0 times 2 plus 2 times 1, which is 2. Oh, no, that's not 1, so in.
Nope.
So, what does that leave us with? Well, it leaves us with D equals 2, C equals 0, A equals 1, in which case, oh noes, the same thing's going to happen. We'll get 1 times 2 plus 2 times 0 equals 2, not equal to 1.
Oh,
Nah.
That was scary.
I kind of made a mess up here on the board, mainly for dramatic effect. But the moral of the story is there is no A, B, C, and D combination that will satisfy all of these equations simultaneously.
I'm clapping in my head.
Thank you. And there's lots of ways you could arrive at that result. Andrew, I've pondered what you were saying, and I think what you're saying would work out as well. But basically, no matter how you slice it, eventually you're going to run into contradictions, and you can get 3 of these equations to be satisfied, but getting all 4 is not going to happen. So that tells us there's no factorization of this thing into quadratic factors. Combine that with the fact that it has no linear factors, means it's irreducible.
Would there be a side factor if it were over the real small?
What do you? Well, what does the reals mod 3 even mean? Okay, so tell me, what is pi mod 3? Okay. So basically, you're just like mapping into like what, like the real interval from like 0 to 3, including 0 but not 3 or something.
Which is isomorphic.
I mean, you could do that, but I don't think that's going to help you out much.
Well, I just wonder if there are any factors that were not, like, I don't know.
I mean, there's gotta be factors over the reals, because it's a quadratic function. It's more than quadratic, so it will factor in the reals.
Oh, true.
We also said we know this is going to factor as a real polynomial because all real polynomials of degree at least 3 are reducible. We proved that a week or so ago. So what can we conclude from all this? We can say that since g of x bar is irreducible over z mod 3, g of x must be irreducible. Since g of x bar is irreducible, and since the degree of g of x bar equals the degree of g of x, since the degree didn't get smaller by reducing mod 3, g of x has to be irreducible. Yeah, Lincoln.
I feel like I'm suddenly completely missing something. What's wrong with x squared plus x plus 1 times x squared plus 1?
Times what?
X squared plus 1.
So then you would get x to the 4th, plus, let's see, you'd get x
We're
to
gonna
the
get 2x
Oh, there's
squared
2x squared, there's 2x squared.
plus an x cubed plus 2x squared, which is,
Yeah, I just had 2 random. I did not add the x squared term. Gotcha. Okay.
What happens when you do that is your algebra is bad. Get better algebra.
So true.
All right, y'all ready for some actual field theory, Galois extension type stuff? Not quite the response I was expecting, but I'll take this.
What response are you
Oh,
expecting?
we went beyond his expectations.
Yay or meh.
See, I thought you.
I wasn't quite expecting exactly. Ooh.
Or in z mod 3.
Oh, this is going to be great.
All right. So everything that we've been doing so far has been building up to what's that?
2, 2, 2, 2, 4. Whoa. It's the 22nd of February.
Oh, the date. I'm like, what? Where? I see any twos on the front page.
I added 2s to the front page.
Okay. So everything we've been doing has kind of been building up background for what we're going to be doing going forward. So like all of our properties of like having polynomial rings over fields be Euclidean domain. That's going to be super important. Things about determining whether or not certain polynomials are irreducible over certain fields. That's going to be super important for us. Going forward, what we're ultimately going to be doing is we're going to be building fields inside of fields inside of fields and looking for ways to connect the ideas from fields inside of fields inside of fields, ultimately to subgroups inside of subgroups inside of subgroups of something completely different. Got a ways to go though for you. So first of all, field extensions. Intuitively, field extensions is just a little field living inside of a big field. Book gives a more technical definition slightly that's basically covering all its bases. Which is to say, we're gonna let K and L be fields with a 1-to-1 homomorphism phi going from K to L. And if such a thing exists, then we say L is a field extension of K. Denoted L colon K.
So that is phi a field extension of K?
L is the field extension of K via the mapped phi.
I'm just looking back.
K and LP fields with the one-to-one homomorphism.
There's the colon.
Oh, I see what you is he talking about? So, practically, and in 99% of the cases we're going to be looking at this semester, we're just going to look in the case where K is a subfield of L.
Not all of them.
But what? I'm going to ignore that. So, why do we say that this is practically saying the same thing? Well, first of all, if K is a subfield of L, how can we find some one-to-one homomorphism from K to L? If K is literally just some subset of L.
Just use the identity function.
And just take some element A, map it to itself. Map A as an element of K to A as an element of L. That's a homomorphism. That's certainly one-to-one. It very probably is not onto, but we don't need it to be onto in order for our definition here to hold. And on the flip side, if one-to-one homomorphism phi from K to L happens to exist, then I claim K has to be isomorphic to some subfield of L. How can we show that K would have to be isomorphic to some subfield of L?
Well, we have this lovely one-to-one homomorphism, so we just take what it maps onto, and then we set that as a subfield of L, and then not only is it one-to-one, it becomes onto.
Yeah. In other words, we just restrict our codomain of this map, so that instead of mapping into all elements of L, we just map it into the image of this. So we could say then phi from K to image of phi is an isomorphism. Why? Because it's onto, and it's still going to be one-to-one in a homomorphism. Hence, K is isomorphic to a subfield of L. It does not necessarily mean K is itself a subfield of L, but what this does say is that it's mathematically the same, in air quotes, as some subfield of L. And so that's why I'm saying this definition involving one-to-one homomorphism, it's pretty much intuitively saying the same thing as K is a subfield of L. It either is a subfield or it behaves exactly the same as some subfield of L.
Why do we know that the image is closed again?
Why the image is closed under
Like,
what?
why the elements that get matched to an L by phi, why like those elements would constitute a subfield with closure?
Because properties of homomorphisms.
Okay.
Basically things like if, like you could say like if, I don't know, L1 and L2 are both in the image of phi, that would imply L1 is equal to phi of some, I don't know, K1, L2 is equal to phi of some K2, which would tell us that L1 plus L2 would just be phi of K1 plus K2. So like that's how you could show, for instance, the image of phi is closed under, let's say, addition. By the fact that like if two things are in the image, the sum kind of by construction has to be in the image, and same and replace pluses with times, and the same is true for multiplication. Does that answer your question?
So the only special thing about field extension is you can use it to describe things with completely different elements.
Correct,
and
but that
as
mathematically
long as they're-
behaves the same.
yeah, okay.
90+% of the time in this class, at least one of these is going to be the rational numbers. 99% of the time in this class, K is going to be a subfield of L. But since the book throws this out as its definition and not just saying K is a subfield of L, I thought I would give this and didn't just talk about like why is that practically the same thing. Questions or comments about that? Seeing none, the motion passes. All right. Vector spaces. It's been a while. It's don't really come up much in 410, and we haven't really talked about it in this class. But it's going to be important for us going forward because we want to have a vector space. We want to define a vector space structure on a field extension. Specifically, what we can do, and here I'm already going to cheat and start just saying K is a subfield of L. What we can do is to say, given some field extension L over K, we can define a vector space structure where K, where L becomes a K vector space. Holy moly! So,
You're supposed to know what a K vector space is, or that's.
we're about to find out. So, think back to your Math 310 days. Depending on who you had for Math 310, Andrew, think back to whenever you first learned linear algebra. Let's say I've had at least a couple of them. I'm going to get to teach linear for the second time this fall.
I had this like 3 years ago, so.
Yeah, what's a vector space?
Vector space is a space with a vector at every point.
I'm sorry I asked. So usually in Math 310, those of you who had me for instance, pretty much in that class we would always talk about real vector spaces. And real vector space is made up of vectors, which is just some collection of objects. So for instance, in Math 310 you probably saw at some point something like R3 is an R vector space. So you got vectors and you have scalars.
So yeah, a ring with scalars.
Yeah, to answer your question, which I'll come back to, the scalars are coming from K.
Okay.
So what are the two things you can do in a vector space with vectors and scalars, Lincoln?
Vector addition, scalar multiplication.
Yeah, we can have vector addition. So for instance, we have a way of adding two vectors to produce some other vector, like 1, 0, 1 plus 2, 2, 2 equals 3, 2, 3. You can add two vectors together in a vector space. You can also do scalar multiplication, which means you multiply a vector by a scalar. So for instance, we could take the scalar, Matthew, give me a real number.
24.
A bit big, but I'll take it. 24 times the vector 1, 2, 3, and we get like 24, 48, 72, for instance. There's vector addition. You can add two vectors in a vector space, and you can multiply a vector by a scalar. Where that scalar, in Math 310 at least, was always coming from the real numbers, always some R. This class, our scalars can come from whatever the field K is. And our vectors are going to be elements of L.
Oh my.
Those two should not sit next to each other.
This one?
Those two should not be in the same class or attend the same college.
Wait, so how do we know it's going to end up being I mean, how do we know this? At least with saying is k be defined as multiplication in L for v equals L, k, or v, sorry, v is an element of L, k is an element of k. Like, how do we know it's going to stay an element of
L.
Yeah.
Because we're assuming K is a subfield of L, so every element in K is necessarily in L, so thing in K times thing in L is the same as thing in L times thing in L, which by the closure of L has to be an L. So let's write some of this down. So that's how vector addition works in R3 as an R vector space, where here our vectors are going to be elements in R3, and our scalars are going to be elements of just plain old vanilla R. Hence why we call it an R vector space, because the scalars are coming from R. Here, our vectors are going to be elements of the big field, L, and our scalars are going to be elements of K.
I don't know if you know which one came first. This is why we use K for field or K for scalar. One or the other was the.
Yeah, I'm not sure which first, but there is very much a correspondence.
So,
Technically, the real definition of a vector space is it's a module over a field. Module is not a term we've encountered in this class, nor do I expect we will. Take representation here if you want to learn about modules. But essentially, the definition of vector space means the scalars are all going to be elements of some field. That's kind of how vector space is generally defined. And back in Math 310, you probably saw a laundry list of like 10 properties that a vector space has to satisfy. Things like if you add two scalars, you can get a scalar in the same thing. All of those properties comes down to, a lot of those properties come down to the fact that the scalars are coming from some field.
so it says given a field extension.
Mhm.
So does that mean that, but L is not defined without K?
Well, K is just some subfield of L. Again, I'm using the practically bit down there. So let's look at an example. Let's do a couple examples. See if that clears up any confusion. All right, we've seen a lot of fields at this point, but we haven't really seen many examples of fields being subfields of other fields. What would be an example that we've seen of one field living inside of another field? Like
Q and R.
Q and R. That's certainly one. So we could look at the real numbers as a field extension of the rational numbers. So what would a computation look like there? Well, basically our vectors are going to be real numbers. Our scalars are going to be rational numbers. And we can take linear combinations and take and then vector plus vector is just going to be adding real numbers. Scalar multiplication is just going to be multiplying a real number by some rational number. So for instance, let's say we wanted to take, 5, 6 times pi plus negative 10/3 times 1 minus square root of 2. Here, this is going to be an element of R, a vector. This is going to be an element of R, a vector. These are going to be the scalars, elements of Q. And when we combine all these together and get, 5 pi over 6 minus 10/3 plus 10 root 2 over 3, when we combine all of these, we're going to get some element in R, a vector. So this is just regular old real number multiplication and addition, but essentially what we're doing, if you think about it in vector space language, is we're taking the vector pi, multiplying it by the scalar 5/6, doing the same thing here, So this multiplication is scalar multiplication. This multiplication is scalar multiplication. This addition is vector addition. And we're just saying multiply scalar by vector to get vector. Multiply scalar by vector to get vector. Sum of two vectors is a vector. Just like how in Math 310, we were doing stuff like 3 times 1, 2, 3 plus 4 times 0, negative 1, 2, and getting 3 to 17 as a result. We're just doing combination, scalar multiplication, and vector addition. Eleanor.
What would a basis for R look like?
Oh,
Wouldn't it have to be infinite?
that's a tough question. I'm gonna come back. I'm not gonna answer that right now. Hart?
Is there a sense, I kind of have two questions, is there a sense of magnitude with this vector space, and is there a sense of distance?
Doesn't have to be a sense of distance.
Like if there, like if you think about the unit, like basically what you said, is there like a unit vector? But that's also, can that both be a scalar and a vector though?
Well, and in R, all of
One
them-
as an element of the reals would be a unit vector. One as an element of Q could be considered as a unit scalar.
But aren't all the elements unit vectors in R?
So what would
Well, it depends on how you're defining magnitude.
yeah, so what would the magnitude of 5/6 pi be?
5/6 pi.
5, 6, 5.
Oh, geez, okay.
Also, something to keep in mind, we're not defining any notion of magnitude here. Depending on what your K and your L are, it might not make sense to talk about like what is the size of something. Like if I were to give you like Z mod 3, for instance, as the overall field, what is the magnitude of 2 as an element of Z mod 3?
Oh, yeah, because it's like, well,
Is it
it's
2? Is it
it's
5?
like a bounded space, yeah.
Is it 8? Is it 11? Is it 14?
Yes.
These are not all the same. They're the same as elements of Z mod 3. They're not the same as elements of R, which is where you would typically consider magnitudes to live.
Does that mean that
Just
there
because we have a vector space doesn't necessarily mean we can define magnitudes.
does that mean that there are spaces where you can specifically?
Yeah,
Also,
Like, I mean, is there a way to like generalize it?
And-
yeah, normed vector spaces.
Oh, okay.
okay, so what about vector spaces that have direction then? Because
Gosh, you all are trying to make my abstract algebra class into an analysis class. Or topology class. I want to look at these algebraic things and you're all like, well, what about the geometry of the space? You're right, we can define in general you can, that's a much harder topic. I don't want to spend too much time answering that question now, but there are ways that you can, for like an arbitrary vector space, try and define norms on it and weird stuff can happen.
Make it non-Euclidean.
Very much so.
Oh,
So that's one example of like how you could form a vector space out of field extension. What's another field extension other than R over Q? There's really only I think one other one that we've really seen or talked much about. James?
Z over R.
Z over R. Tell me something. Are the integers a field?
I'm sorry, I didn't mean Z, I meant C.
Oh, you meant C.
that's what I heard.
That's not what I heard. Yeah, they take complex numbers of the reals. Or in this case, your vectors are going to be complex numbers. Your scalars are going to be real numbers. So we could do something very similar. Take like, for instance, I don't know, pi times 1 minus I plus 6 times 2I. This would be a case where, again, this would be a scalar coming from R, smaller field. This would be a vector. The scalar multiplication is you just multiply pi times 1 minus I like you normally would in the complex numbers. Get pi minus pi I. So that when we simplify, we get a pi plus I times
That's not a number.
negative pi plus 12.
Hey, this is a fun one. Because the basis only has dimension 2.
Has a vector. That would be a vector.
What?
So it's
complex numbers.
1 minus I is one vector or two vectors?
1 minus I is a single vector because it's a single element of the complex number.
Because the vector is.
You could break it up into the sum of two vectors. You could write it as this. You could take vector 1 minus I and write it as the sum of 1 plus the vector negative I. Just like we could take this vector and write this as the sum of 1, 0, 0, and 0, 2, 3, for instance.
Okay.
So you could think about it as the sum of two vectors or as a single vector, just like you could that. It comes down to a frame of mind. Like,
I have another field extension,
oh, okay.
C over C.
C over C.
So
That works.
Yeah.
Your vectors and scalars both come from the same thing.
And then you
Oh.
expect run free.
Or if you want one we actually did in 310, R over R.
Like,
Wait, can we
you
just
just
over
made
Q?
Seamus cry.
C over Q? Yeah, we can do C over. We can do C over Q as well. You just have complex numbers as your vectors.
Yeah.
Your scalars would be rational numbers, but that would be fine. If you really wanted to get saucy, you could do something like Z mod P over Z mod P. In which case, your scalar multiplication is just multiplication mod P. Your vector addition is addition mod P.
But are they different P's?
No, there's,
Same P.
or else the,
Well, otherwise, because one needs to be a subfield of the other.
Right.
And subfield implies it's the same operations going on in both of the
Right.
cases.
Oh, good. I'm glad you can't do that with different P's.
So,
wait,
any other questions or comments about what this vector space structure kind of looks like?
what if we did, the real polynomials to the rational polynomials?
Ooh. Those aren't fields, so we can't do that.
Uh,
That would be fun if we could.
And
If only there was a way of taking real polynomials and making them into a field. If only we could find, say, the field of rational polynomials. Stay tuned for the next packet. So, what do we do with vector spaces?
so many fun things.
So many fun things. But the one I'm interested in today, you can look for bases.
Yeah, that's fun.
I was gonna say, a couple of
bases.
I was gonna say, you all are chopping at the bit to start finding bases, so let's talk about that.
it's kind of the Seamus space.
So, as a reminder, because for some of you I know it's been a while, basis is just a spanning set that is linearly independent. Spanning set meaning anything in your vector space can be written as a linear combination of those basis elements. Linearly independent basically means none of them can be written as a linear combination of the others. Do y'all want me to write this out on the board, or?
Well, I'm just, for the linear independence
Good
parts, it says the only solution in B to the equation a1b1 plus a2b2 plus an bn equals what? 0 equals 0,
Oh, that
right?
should be equal 0 in there, yeah.
Okay, that's what I thought, but I was like, am I?
That is not an equation, that is just a polynomial. Yeah, put a 0 in the line, in the equation directly under where it says linearly independent in bold, please. So, quick example. Let's look at R3 as an R vector space. No, R is not a subfield of R3. But, just give us a good old Math 310 reminder of what vector spaces, bases look like. So what would be a basis? A set of vectors that's linearly independent and that spans all of R3.
Would it be 1, 1, 0, 0, 0, 1, 0, and 0, 0, 1?
Hey, the standard basis, thank you. That's why I didn't call him Lincoln, because I knew he would not give me that.
I wanted to be boring and make this actually move on.
Yeah, so one way of forming a basis would be the standard basis.
You could also just choose 3 random linearly independent vectors.
Any 3 linearly independent vectors would get the job done. Any 3 vectors that span R3 would also get the job done. Typically, E1, E2, E3. So that's one. What's another one? All right, Lincoln, give me another one.
20, 24, 0, 0, pi, pi, 0, and 27, 27, 27.
Believe it or not, that's actually less scary than what I thought you were gonna give me.
Yeah, there's no like e minus pi in there.
You could, yeah, basically this is gonna span all of R3 because you could write any vector in R3 as some linear combination of these three vectors. And by the way, when I say linear combination, I mean scalar times this plus scalar times that plus scalar times that.
And that scalar can also just be 1/24, 1 over pi, and 1 over 27.
Well, yeah, if you want to get like if you want to get ones in every entry. These also are linearly independent in that none of these can be written as a linear combination of the other two. Or equivalently, if you had some equation of this form, if you had some equation that looked like that, the only values you could plug in for A, B, and C that would, the only values you could plug in for A, B, and C that would satisfy this equation, are they all 0? So that's what makes this a linearly independent set. I mean, you could say C has to be 0 in order for the third coordinate to be 0. Once you know C is 0, you could say B has to be 0 for the second coordinate to be 0. And once you know C and B are both 0, then A has to be 0 for the first coordinate of the summing amount to 0, for instance.
That last 0 looks like a delta.
It does. I thought the same thing. I'm not erasing it. But there's a whole lot of bases for R3 out there. You can check if a set of 3 vectors forms a basis by putting them into a matrix, row reducing, see if you get the identity matrix. And there's like a gazillion different ways you could check to see if a set of vectors forms a basis in R3. But what do we know about all bases in R3? What do they have in common?
You have 3 vectors?
There you have exactly 3 vectors. That's kind of a key property of vector spaces, is that any two bases over the same vector space always have the exact same number of vectors. And we call that number the dimension of the space. So the fact that, excuse me, sir. So as a real vector space, we could say that the dimension of R3 is 3. We could say that the dimension of Rn, Eleanor,
Yes. Is n.
is n. Because any basis for Rn will have exactly n vectors. I'm not going to go through it and reprove that now, but that's something you should have seen back in your 310 days. That any two bases for the same vector space have the same number, contain the same number of vectors. So, let's look at these field extensions. These are vector spaces. You should be able to form bases here. Let's do that. So, if we flip to the next page.
Something tells me CR is going to be easier than R.
Oh, yeah.
Something tells you that. Well, on a completely coincidental note, I want to start with CR as our first thing of the two. So let's look at what's the dimension of C as a real vector space. So in other words, what would be a basis of C as an R vector space?
1 and I.
1 and I. That's a linearly independent set. Neither of these is a scalar multiple of the other, mainly because they're scalars that have to come from R, and no real number times 1 will give you I, or vice versa. It's a spanning set for the complex numbers, and that any complex number can be written in the form some scalar times 1 plus some other scalar times I. So it forms a basis. And so the dimension of C as a real vector space is going to be 2. And we denote that like this. So this is a shorthand notation for the dimension of C as an R But Dr. Gerstle, that looks an awful lot like something I saw in Math 410. I can't remember quite what it was.
I don't remember what it was.
Aren't you special? What was it?
It was the index of a subgroup in a group.
Oh, and pray tell, what is the index of a subgroup in a group? What does that refer to?
It's the well, I remember what it's equal to in finite cases. The exact definition I don't remember off the top of my head.
Oh, what a shame.
Yeah.
Does anybody remember what the index of a subgroup in a group referred to?
If like the left cosets of the subgroup should partition the group, and it's like the number of cosets that is.
Yeah, it's the number of cosets that subgroup has. And yet we're using the same notation to make your life more difficult.
Sadness.
Or perhaps we're using the same notation because there's a connection between these ideas. The fundamental theorem of Galois theory. Maybe there's, I don't know, some permutation group of how many ways are there to permute the elements of C while keeping the real numbers the same, and that forms a group somehow. And anyways, there's the reason why this notation is the same. I'll just tell you for now is because there is a very much a strong relationship between dimension of C as an R vector space and something going on involving subgroups. Instead of the what?
The degree.
It's not the degree, it's the dimension.
Degrees is polynomial.
Well, it's the degree of the field extension. We're going to call it here in a second. Actually, at the top of the page it says that. So another way to say this is the degree of the complex numbers as an extension of R.
Next you're gonna call it the power or something, I don't know.
Don't be ridiculous. That's mine. So yeah, degree of a field extension is just if you make this vector space structure, what's the dimension of the corresponding vector space? In this case, C as an R vector space. Questions or comments about that? Andrew, by the way, I'll mention, you picked 1 and I as your basis. That's what I did. That would be what I would call the standard basis for C as an R vector space. There's others you could have picked. Could have also done something like
Pi root 2i.
pi and what?
Root 2i.
That would work.
If you don't one plus pi and sorry, 1 plus I and 1 minus I.
1 plus I and
1 minus I.
and 1 minus I. That would work as well. Any two elements, as long as
They're not.
neither of them are a real scalar multiple of each other.
Let's see, what about 1 plus the square root of 19i divided by 2?
Okay, Abby, no.
Wait, wasn't that one that
Yes,
joined with
that was
Yeah. Oh, I see. That's what you were thinking of. I mean, yeah, you can make that a basis element. That's a complex number.
Plus pi.
But just like how an R3 has an R vector space, any basis always had 3 elements. Any basis of C as an R vector space will also always have 2 elements. All right, because you all want it so badly. How are we doing that time? Yeah, good. Let's look at this one.
This is Seamus's favorite.
No.
What would a basis look like for the? So here we need a basis of the
The Seamus space.
of the real numbers as a Q vector space. Completely upending, because here now the real numbers are no longer your scalars; they're your vectors, and the scalars are rational numbers.
So dear science.
Perfect.
Would the basis be 1?
Just 1.
It could be just
How do you
1.
get the square root of 2?
How do you get the square root of 2?
Or 3,
Or
or 5, or 7. All
No,
those
you
square-
can-
I know, all those
It
square-
has
might
to be
be,
a-
One, the set containing 1 and all positive irrational numbers.
All positive irrational numbers?
Not
That-
yeah.
That would not be linearly independent.
Oh,
Because, for instance, square root of 2 and 3 square root of 2 would both be in that set, and those are scalar multiples of each other.
Almost.
But we could do, for instance, 1. How about pi? Pi is some vector in R that we would need. You know what's not a Q multiple of pi, though? Pi squared.
Oh.
Oh.
You know what you can't write as a linear combination of 1 pi and pi squared? Oh, but we also need E because, well, actually this is not known, but it's strongly suspected that E is not in this family. What's that?
We definitely need the square root of 2.
Yeah, we'll definitely need square root of 2.
Yeah, but Dr. Bristol.
Oh, we'll also probably need, you know.
Yeah, but you forgot pi to the power of pi.
Oh,
Oh, that's true.
Yeah.
heaven forbid I forget pi to the power of pi.
Yeah.
What about pi to the power of pi to the power of pi?
So,
Well, see, if you start doing that, then you get like E.
So, what do we
times
think
the
this is?
log base pi of
I
E.
think it's insane.
Is it?
it's an infinite dimensional vector space.
I hate that so much.
And it's uncountable.
I knew I
Yeah,
hated
We've
it.
got that shameless space.
Yeah. All right. So I actually have a question for y'all. Who here has taken real analysis,
In
I'm in
the
it right
process.
now.
or is taking real analysis currently?
I should ignore that my hand is down.
Okay. Out of those of you without your hands up, who has not seen countability in like uncountable over sets, etc.? Jackson, Andrew, you kind of have somewhat.
Yeah, so what?
I bring this up because
It's uncountable.
a lot of what the book does in this section, where in the next section, revolves around countability arguments. For instance, proving the existence of transcendental numbers. I'll try and do a little bit of review along the way. Because it sounds like all of you at least have a little bit of familiarity, at least, with countability arguments, but this is not a real analysis course. I recognize that it doesn't have real analysis as a prereq. I don't expect you all to be masters of dealing with countability in this class. But yes, this would be an uncountable infinity.
I knew it.
For instance.
Not countable. Wait, which uncountable?
Well, it's
Oh my
all
gosh.
reals.
It has to
Because like we don't have 3
Because
root
there
2,
are
but it's
infinite
still.
Well, I don't know.
uncountable
Well, there are. It can't be. It's at least at most the uncountable. That's the size of the real numbers.
Okay.
Do you believe that there's an infinity size between the reals and the rationals?
Well,
Parker?
I mean, there may or may not be.
What's your take? I was gonna say, what's your take on it?
It's whatever
I
you
don't-
want.
I don't-
Whatever you want.
It's the same as the number of real numbers.
Out of curiosity, if the degree of L over K is uncountably infinite, is L always at least one size of infinity larger than K?
Yes.
Yeah, that's a good one.
Yeah, that actually, that might seem silly, but it actually is a good and somewhat non-trivial question, and the answer is yes.
And then do we know about countably infinite degree?
Yeah. Well,
If that's you.
if L over K comes out to countable infinity, does L have to be a higher degree of infinity than K? I think the answer to that is no.
Right, yeah, that's what I suspect.
Do I have a good counterexample of that off the top of my head? Not off the top of my head.
What about the density of K in L?
The density, what on earth does that even mean?
Well, so Q is dense in R.
Yeah? What does it
Does
mean?
that have anything to do with,
Here's my question. What does density mean in a purely abstract algebra sense?
that's an excellent question.
So, in specific cases, you can do that. But over arbitrary fields, it might not make sense to talk about density, because density relies on somehow having some notion of distance, which we don't necessarily get over
That's what I said.
arbitrary. That being said, these two examples, you can look for and talk about like density and ask like, is R dense in Q? Or is R dense in C? No. Is Q dense in R? Yes.
Only because we've been studying these for 100 years.
Say what?
Only because we've been studying these for 100 years.
Yeah, because these are kind of the classical examples and there's lots of interesting analysis questions to ask about these. But not all fields you can do that, so we're not going to be making those sorts of arguments in this class. Alrighty, so when we come back next time, we're going to prove a theorem that looks suspiciously like Lagrange's theorem.
Oh, yeah.
And from there, start talking about different types of field extensions. More than just these two. Hope y'all have a good one. See you all on Tuesday. Let me know if you all have anything you don't want me telling your parents on Saturday.
Just a quick question. I'm struggling to find the recorded lectures on Canvas.
I have really quick here. I've just been sending Lydia the links. Send me
Okay.
an email to remind me, and yeah, I can keep those.
Okay, and then I was also wondering if it's possible to say get the extension to the next more Thursday. Okay, yeah, thanks. It's just, I just
Yeah,
haven't
it's
tried
mainly
it.
it's mainly focused on the two classes that you missed.
Yeah, so I got like, yeah,
Look at the camera.
I missed pretty